Understanding the component solver depends on some understanding of the kind of problem it solves. As an example, we'll use this simple situation. The target is stationary, and own ship's course and speed are constant. With the ship's movement, range changes continuously. Target bearing, too, is always changing. Furthermore, not only are range and target bearing changing, but the rates at which they change are not constant. To illustrate, these 4 ship positions are spaced at equal intervals of time. During the time between A and B, the change in range is greater than it is during the time between C and D. Thus, the rate at which range changes is not constant. And note, too, that between A and B, the change in target bearing is less than it is between C and D. Thus, the rate at which target bearing changes is not constant. Solving the fire control problem requires continuous information of the existing rates of change. This is a vector problem in which we know own ship's course and speed, shown here by the length and direction of its speed vector. We also know the line of sight to the target. The rate of change in range, or range rate, is the component along the line of sight. The rate of change in target bearing, or bearing rate, is the component perpendicular to the line of sight. Comparing vector diagrams at 2 ship positions, the difference in the components of bearing rate, and also the difference in the components of range rate, show again how these rates may change, even though ship's course and speed are constant. These rates also change with a change in course. They also change with a change in speed. The problem is how to provide continuous, up-to-the-moment solutions. This is done by the component solver. It continuously forms the vector diagram, measures the components, and transmits their values to other parts of the computer. To see how it forms the vector diagram, we'll start with the speed vector, considering first its direction. Direction is measured relative to this center line, which represents the line of sight. The speed vector lies along the slot in the vector gear. An input gear turns the vector gear. Direction of the slot relative to the center line reproduces the direction of ship's motion relative to the line of sight. Now let's see how vector length is obtained. Under the slotted vector gear is a cam. The cam surface is a spiral groove cut in the face of a gear. The cam is positioned by this input gear. A follower, with a projecting pin, rides in the groove. The pin extends up through the slot in the vector gear so that pin and follower can move only along the slot. Ship's speed is entered through this input gear. With a transparent vector gear, you can see how the spiral groove moves the follower and pin along the slot. The distance from gear center to pin is the length of the speed vector. When the speed is 0, the pin is at center. At low speeds, the distance from pin to center, the vector length, is small. As higher speeds are introduced, the vector increases. The vector is maximum when full speed is reached. Now that we know how the speed vector is produced, we next want to see